introduce our speaker today, Dr. Ilyos Rabbimov, who is going to talk about language modeling. So I did Google on language modeling because I'm not familiar with this area. It's looked like language modeling determines word probability by analyzing text data. And they interpret this data by feeding it through an algorithm that establishes rules for context in natural language, and then the model applies this rule in language tasks to accurately predict or produce new sentence. So I think this is a topic in which we should all be deeply interested because technology actually could accurately predict or produce new sentence. Before this, we might don't even know that technology can do this kind of task. So we hope that our speaker, Dr. Ilyos Rabbimov from Samarkand State University, it's very far from us, about more than 5,000 kilometers, could explain to us from the beginning about language modeling. And let me introduce to audience that he is an award-winning and received patent for 2 products. If I'm not mistaken, it's on Electronic Journal of the Rating Control System and a software package for lexicographic and statistical analysis for literary text written in Uzbek, which was issued in November 24, 2017. So you are expert in this area, so we do hope to hear from you about language modeling from the beginning, because maybe there is someone out there might interested to know about language modeling in the context of Uzbek language. So I pass the presentation to you, Dr. Ilyos.
Thank you very much for introducing and all the information.
Yeah.
Can you see my presentation?
Sure.
Today I'm going to talk about the language modeling on the example of Uzbek language. Outline of this talk consists of this part. And first, I try to explain what is the language model and where I use it, and n-gram language models, a neural language model, and word embedding for Uzbek. Language modeling is a task of predicting what word comes next, and for example, as students open their books, laptops, exams, minds. More formally, given a sequence of words x1, x2, etc., x, t, I compute the probability distribution of the next words x t plus 1, denoted by this the probability expression where x t plus 1 can be any word in vocabulary v. A system that does this is called a language model. You can also think of a language model as a system that assign probability to pieces of text. For example, if we have some text, then the probability of text, this text according to the language model is calculated using this following formula. Every day we use a language modeling. For example, in our phone have predictive typing and text suggestion in any search engine system, Google, Yandex, and etc. And speak recognition system, handwriting recognition, optical character recognition, machine translation, and spelling correction, grammar checking. Also, and natural language processing, many tasks used language modeling. For example, authorship identification, part of speech tagging, summarization, information retrieval, text classification, and sentiment analysis, opinion classification, and question answering system, and etc. N-gram language models. Language model, how to learn to predict next word, and learn an n-gram language model, and this is the most popular language model in NLP. They are described, and the students open there, and next word need to predict via language model. And n-gram is a chunking of n consecutive words, and they are given unigrams, bigrams, trigrams, and 4grams. Unigrams consist of one words, and their students and open it there. And bigram consists of two words. The students open it there. And trigrams, they consist of three words, and 4grams consist of four words. Main idea of the language n-gram language models collect statistics about how frequent different n-grams are, and to use this to predict next words. First, we make a Markov assumption for x t plus 1 depends only on preceding n minus 1 words, and there are n minus 1 words, and this is assumption x t plus 1 is will be predict. A probability of an n-gram compute this using this formula, and probability n minus 1 gram is compute this formula. We get these n-grams and n minus 1 gram probability by counting them in some large corpus, and we counting and sequence of words in the corpus. This is a statistical approximation. Suppose we are learning a 4-gram language model, and this is a given sentence. We choose and 3 and 4 is a predicted words. This is called condition on this. These words discard, and probability W, and students open there. First we count students open there W, and this pattern in context, and then counting this pattern in all corpus and divide. For example, suppose that in corpus students open there and occurred 1,000 times in our corpus. Students opened their books occurred 400 times, and probability is books, and they are 0.4, and students open their exams occurred 100 times, and then probability exams equal 0.1. But you can see the sentence as if protector started the clock, and there and exams need to predict, but in our this probability high from exam. Should we have discarded the product context? In sparsity problem with n-gram language model, first sparsity problem. What if students open their W words and never occur in data? Then V and W was probability 0, and then probability is equal 0. Solution, partial solution for this, add small delta to count for every W belongs to V vocabulary. This is called smoothing. Second sparsity problem, what if students open there never occur in data? Then we can calculate probability for any W. Solution for this, just condition open there instead of students open there. This technically is called backoff. Also, increasing n makes sparsity problems worse typically we cannot have and bigger than 5 grams. And the next problem is storage problem with n-gram language model. Storage need to store count for all n-grams used in the corpus. And increase n or increasing corpus increase model size. You can build a simple training language model over the 1.7 million word corpus. For example, Reuters consists of business and financial news in a few seconds on your laptop, and they are 3 gram, and first 2 words today there, and the next word. For the next word, language model get probability distribution and the words and probability score. And they have problems, positive problem, not much granularity, and because it's probability distribution score and same. Language model. We can generate text using an n-gram language model. You can also, for example, this today is there. This is condition on this, and get probability distribution using n-gram language model. And we select this, and today is the price, and we apply a 3 gram model. And there is a 2 words and 3 short words predicted using a language model. There are candidate words and probability distribution score. And you can also use language model to generate text like this. You can see, and this text surprisingly and grammatically, but incoherent. We need to consider more than 3 words at a time if we want to model language well. But increasing n warrants a sparsity problem and increase model size. This is inconvenience. Training and test data. The language model must be trained on large corpus of text to estimate good parameter values. Model can be evaluated based on its ability to predict high probability for disjoint test corpus. Ideally, the training and test corpus should be representative of the actual application data. May need to adapt to general model to small amount of new data by adding highly weighted small corpus to original training data. Next type of language model is a neural language model. This language model is very popular in NLP. How do we present the meaning of the words? Meaning is the idea that is represented by word and phrase. The idea that person wants to express by using words, signs, etc. The idea that is expressed in work of writing, art, etc. This definition obtained Webster Dictionary, and commonest linguistic way of things of meaning, the signifier of symbol and significant of idea of things. This is I call denominational semantics, or also call it mathematical semantics. How do we have usable meaning in computer? Common NLP solution usage like WordNet and thesaurus containing list of synonym sets and hypernym set. Hypernyms is the relations semantics. Synonym sets contain the good. They are described synonyms of good, and hypernames of panda described hair. Problems with resource like WordNet. Great as a resource, but missing nuance. Proficient is listed as synonym for good. This is only correct in some context, but some contexts not correct. missing new meanings of words, and impossible to keep up to date. And we know words and new words into language. And next problem, subjective, and next requires human labor to create new and adapt. Can it compute accurate word similarity? Presenting words as a discrete symbol. In traditional NLP, we regard words as discrete symbol. For hotel, conference, and motel, a localist representation. Such symbol for words can be represented by one-hot vectors. These vectors consist of one and remains of zeros. Vector dimension equal number of words in vocabulary. For example, vocabulary have 500,000 words, and then hotel vector dimension is 500,000, and it is very large. Problem with words and discrete symbol. Example, in web search, if a user search for Seattle motel, we would like to match documents contain Seattle hotel. But and motel and vector here and hotel vector here. These two vectors are orthogonal. There is no natural notion of a similarity of one hot vector. There have some solution. Could try to rely on WordNet's list of synonyms to get similarity, but is well known to fail badly, incompleteness, and etc. Instead, learn to encode similarity in vectors themselves. First, said you should know a word by the company it keeps. This is called a distribution of semantics. A word's meaning is given by words that frequently appear close by, and this is one of the most successful ideas of modern statistical NLP. When word W appear in text, its context is a set of words that appear nearby within a fixed window size. Uses the many contexts of V to build up representation of W. There W is banking, and these words nearby words is called context words. And context words will present banking. And word vectors. We will build a dense vector for each word chosen so that it is similar to vectors of words that appear in similar contexts. Word vector, also called word embeddings or neural word representation, and all of them call it distributed representation. Word meaning as a neural word vector visualization, and the vectors of semantically closed words are also mutually close, and semantically closed words located nearby in two-dimensional coordinate system, and you can see here laptop, keyboard, and Xbox monitor, and located nearby, because these words is similar, semantically close. And word vector, the vector corresponding to words are chosen so that mathematically the cosine of the angle between the vectors indicates the degree of semantic similarity of the words corresponding to these vectors, like traditional mathematics. WordVec is a framework for learning word vectors presented by Thomas Mikolov. The main idea of word vectors, we have a large corpus of text. Every word in fixed vocabulary is present by vector. Goes through each position T in the text, which has center word C and context word O. Uses the similarity of word vectors for C and O to calculate the probability of O given C. Keep adjusting the word vector to maximize this probability. Word overview. Example of windows and process for computing probability. This is center word at position T, and this word called also target words or middle words. The outside of context words is this is context words and window size 2. Two words selected and there left side 2 words selected, and probability for each words and will be calculated for each position T and predict context word within a window of fixed size M. Given center word VG, and VG is the target word, data likelihood, and there set is all variables to be optimized. This is probability. The objective function, this function also call it a loss function or cost function. G is a negative log likelihood, like this. The word vector main goal is minimizing objective function or maximizing predictive accuracy. We want to minimize the objective function, this function. We will use 2 vectors per word W for calculate the probability. Probability. There VW when V is a center word. This is UW when V is a context word. This is center words. Corresponding vector for this is context word vectors. Then for center words C and context word O, we can calculate using a softmax function for log probability. Example of windows and process for computing with words. For example, the into P U problems V into we will calculate this probability. This is short form for this one. Probability of these words and these words and these words and these words, target words and context words, and calculate. Exponential makes anything positive, and in softmax function, dot products compare similarity of O and C, U transpose and dot product V. Large dot product means and large probability, and normalize our entire vocabulary to give probability distribution, and because sum of probability need to equal 1. This is an example of softmax function. General expression of softmax function described here. The softmax function maps arbitrary value xe to a probability distribution P. Max because amplifies probability of largest xi. Soft because still assigns some probability to smaller xi. Frequently used softmax, and very frequently used in deep learning techniques. Word embeddings for Uzbek. Word embeddings. This is one hot vector for cat, and this describes the word, and neural language model created word embedding vector corresponding to cat, and finally word embedding vector for cat, and we can obtain word embeddings represent each word with a low dimensional vector. For example, 50 dimensional or 100 or 300. Word similarity equal vector similarity. The KID predicts surrounding words of every word faster and can easily incorporate new sentence, documents, or add word to the vocabulary. We can extend vocabulary and extend vocabulary word vectors. Represent meaning of words. Word2Vec have two basic neural network models, and first continuous big of words, and second skipgram. Continuous big of word use a window of word to predict the middle word. Skipgram use word to predict surrounding ones in window. Both of them consist of three-layer neural network, shallow neural network, and first layer input layer, and projection, and hidden layer, and output layer. SIBO goal is predict target words from context words. Skipgram's goal is predict context words from target words. Word2Vec was created and published 2013 by the team of researcher lead by Thomas Mikhailov at Google. Word embeddings for Uzbek. To create word vectors for Uzbek language, we have collected corpus from most popular news sites in Uzbekistan. Number of tokens in corpus, approximately 47 million. This corpus used to train our language model. The word embedding for Uzbek language, the first word embedding language model presented by Thomas Mikhailov, and a second Uzbek fast text language model presented by Kuryazov, and Uzbek Word2Vec CBO and Skipgram pre-trained word embedding models presented by this is our language model. There is vocabulary richness of each language pre-trained language model. As mentioned before, and language model used many NLP tasks, partially opinion classification, text classification, and sentiment analysis. We used this language model for opinion classification of Uzbek text, and the results of opinion classification of Uzbek text from movie review comments from YouTube based on LSTM and word embedding. You can see, and high accuracy obtained when Uzbek Word2Vec Skipgram was used. This word vector presented by us. Thank you for your attention. And
thank you, Dr. Ilyos. It's very good presentation, giving us information on the beginning part of research of language modeling, which give us an information on beginning of the language modeling research on language modeling. So
Yeah.
I open if audience have any question to ask about language modeling to Dr. Ilyos.
Hello, Dr. Ilyos.
Yes,
Hello,
Dr.
can you
Rosma.
hear me? Okay. Very.
Hello, there, Rosma.
Yeah. Thank you. Thank you for the presentation. It's very interesting. It's very eye-opening. I have a question. Now, this neural language model, you've used it for language with Roman alphabets, right? Like A, B, C, and D, and so on. Can it be used for language using other alphabeticals like the Arabic language, the Japanese language, the Chinese language? Can it be used?
Thank you for the question. Very interesting question. Many language has different symbols. And in Arabic, in Uzbek, in Russian, in English, and different from one. So, and neural language model, first we need to create vocabulary. And vocabulary have many words. And each words have one hot vector. For example, the book in vocabulary, the one hot vector like this. This vector input the language model. And hidden layer and output layer. And another language, and for example, Uzbek and Kitap, in vocabulary, these words have also one hot vector, like this. And so, and many different language, this model easily applied.
Okay, is that answering Dr. Rosma's question?
Yes, thank you.
Yes, first we have to create the vocabulary. Any language, we must create the vocabulary for that particular language, and from that vocabulary, then only we can create the hot vector, isn't it, Dr. Ilyos?
Yes, yeah.
Thank you. So this is very powerful tool for modeling, because I missed that part. That you have to create the vocabulary first, regardless of whether you're using Roman alphabets or any other kind of alphabets. It can still be done. Thank you very much, Dr. Ilyos.
Yes,
Dr. Ilyos. Dr. Ilyos, I just want to double check with you what you have produced that is on Uzbek word to vec, isn't it? Using skipgram?
Yes.
That one is the best if you compare with the Mikolov research, isn't it? Just now you show to us the accuracy. Yes, this one. You show to us the accuracy of the word embedding using Uzbek word to vec skipgram. The accuracy is 90.80, which is this is good because you are predicting the surrounding. You use the word to predict the surrounding ones in the window. That one is good as compared to the method of if we predict only the middle word, right? So this skipgram is very good as compared to CBOW, isn't it?
Yes, there and skipgram predict and this is SIBO architecture.
SIBO, yes.
There is skipgram architecture. The same calculation mathematically, but neural network structure different, and SIBO is a predict target words from context words and that surrounding words. Skipgram predict context words from target words, and SIBO and more powerful for middle data.
Yeah.
Skipgram powerful for train very huge data.
I see.
And skipgram more capture and word semantics and meanings than SIBO when trained model with very huge data. There we trained approximately 47 million tokens.
Yeah.
And there is some reason because Thomas Mikolov present this word vector, our word vector collected from our news site, and this word vector trained by using Wikipedia crawling.
Okay.
Used crawling common tools, and Wikipedia have many text, but this is text translated using machine translation technique and programs. But use many of them and not written by user and Uzbek user.
Okay, thank you with the explanation. Again, I open for any question. We have about 10 or 15 minutes more before we finish our webinar. Is there any other question?
Hi, good afternoon. So I'm Sohaila from UiTM. I just want to ask regarding your architecture. Can you go to the slide? Okay. I can see here that SIBO and skipgram use different architecture, right? And from your result, you mentioned that skipgram is better than the SIBO because we have, if we want to have a lot of data. Is it correct?
Sorry, last sentence. I can listen.
Okay,
can you repeat last sentence?
Okay, I can see here that SIBO and skipgram use different architecture because their input are different. Is it correct?
Yes, correct.
Okay. And then you mentioned that based on your accuracy, skipgram is better than SIBO because is it because of we have a lot of data? Is it because of that?
Yes.
Okay, and then
right.
And then do you have any other method that use the same architecture as skipgram? Is there any other architecture that's similar to the skipgram so that we can look into that in order to compare with the skipgram?
Yes, thank you for question. My understanding and this Uzbek word-to-vec skipgram and word-to-vec SIBO and different architecture and neural network, and fast text another architecture, and there used engrams of character engrams. This neural network language model and different than word-to-vec. Also, they have another word-to-vec architecture. For example, GLOVE, Global Vector Representation, presented by Stanford
I think
University researcher.
Because skipgram and SIBO are used for two different purposes, right? Skipgram and
Yes, Dr. Rosma, do you want to add on something on the question? You can go ahead.
different purposes, because one with many inputs, one output. The other one has one input but many outputs here, right? The SIBO
Right.
with many inputs but you produce one output. On the other hand, the
Yes.
skipgram, you start with one input and you have many outputs. So they are being
Yes.
used for different purposes.
Yes.
Yes, you are right.
Can I see one question, Dr. Ilyos? Here, the SIBO and skipgram, this is a very, very simple neural network model, right? You have one layer, right? Probably, if we use more layers, more hidden layers, do you think it will increase the percentage of accuracy? Here, you have only one hidden layer for each network. For the SIBO, you have one hidden layer. For the skipgram, you have one hidden layer, right?
Yeah, thank you. And question, there and one hidden layer, and if you said if we increase number of hidden layer and accuracy perhaps and increase. Yes.
Probably, yeah. Thank you.
Probably, but and there are many problems because there are very huge training data. So and their computing cost. We need to take into account training number of training data and computing costs. And another reason, and if we have huge training data, and then our vocabulary will be and very huge. Then and during training time and increase, and if we add hidden layer, and as Thomas Mikolov and their team and described more detailed reason for why use it one hidden layer.
Yes, thank you.
So,
Yes, I agree with you. Thank you, Dr. Ilyos. Yes.
Okay.
Thank you.
Thank you too.
Okay, any more question? One more question.
Dr. Ilyos, okay, what are the mathematics used in your research? What kind of mathematics you use in your research?
Mathematics?
Yeah, you use vectors, statistics?
Yes, distribute they used some statistics technique here. and probability. Mathematical statistics and probability and linear algebra methods because and there are many computing steps. For example, dot product, many vector and matrix, and calculate gradient descent and etc.
Okay, thank you, Dr. Ilyos. Is there any more question? PM Shukri, you want to add more question?
Yeah, I think that's all.
Okay. So again, thank you for Dr. Ilyos for the presentation and also answering all the question in the Q&A session. It's very good research for us. This is for me. It is new knowledge because this is not my area. But as Dr. Rosma said that this language modeling is an eye-opener to our researcher here. So anyone who interested to collaborate with Dr. Ilyos, maybe Dr. Ilyos can share your email through chat room. And anybody want to collaborate with you, then they can contact you through email. Dr. Ilyos, is that okay?
Yes. Can you see? I will share my email and.
Okay, and for those participants today, please wait for a photo session. There will be Dr. Nomi to handle this photo session. And please open your video. Dr. Ilyos, please open your video as well so that we know.
Yeah, can you see?
Yes, Prof. Exot is also here. How are you, Prof. Exot, after 1 week time?